All right, I'm going live, okay?
Okay.
All right, hello everyone. Welcome to this brand new episode of Corecast. I'm your host, Tim.
And I'm Mikey.
And this is Sahil. Welcome everybody to a brand new exciting episode of Corecast. Before we get started, if you haven't already, do join our Discord channels. You can ask those questions there. And if you're watching this on YouTube, do ask those questions during the episode and we'll get to them and answer them. So without further ado, I guess we've been talking a lot about quantum mechanics, and I just want to know, like, how does this pertain to human beings? Like, in the sense of just does it explain where we came from, or is it too abstracted away? It seems quantum mechanics seems extremely abstract. I guess Mikey or Tim, pick apart my question however you wish.
You go,
Mikey, you
Tim.
seem willing.
Okay, I guess I'll go first. Yeah, I feel like if you just ask like any random physicist just point blank, they'll probably just stare at you and be like, "What are you trying to get at?" But to some extent, I I think this is a fair question, right? Like ultimately,
Wait, let's just say that there has been a lot of talk of, like, in terms of how quantum mechanics relate to humans, like, does it give rise to consciousness? And
okay,
those ideas are, yeah, let's
okay,
not talk about those ideas.
like those are, I think definitively there's a sense in which those are garbage ideas. I think we can quantify to the extent how garbage it is. And that's the reason why when you ask the physicist questions like this, people might just be like, another crazy person trying to like come up with their crazy ideas. But at the end, it is a fair question, right? Like obviously humans, we are curious about our existence and where we come from. And ultimately the laws of nature is quantum mechanical. So there is a very real sense in which our existence has to be partly thanks to quantum physics. I mean, it has to be, right? So there's a
I mean,
story
there's
there.
so many ways in which it is, right? In addition to quantum mechanics, origins of consciousness, there's also the obvious fact that the stability of atoms relies on quantum mechanics,
Yeah,
and that, molecules and, complex chemicals and humans wouldn't be possible without quantum mechanics. But that's a little dry.
that's a
So
dry. Yeah, I would go really grand. I would go really grand because, like let's face it, the as far as we know, the fundamental laws of physics is quantum mechanical. I think this is the closest thing to reality that we have. So that means the entire universe has to be quantum mechanical in some ways, right? So in that lens, the existence of in the entire universe has to be thanks to quantum mechanics, right? And it has to play a critical role, not just like some just like some sideshow, slightly relevant role. No, quantum physics is completely important in the formation of the universe.
Yeah, and we had talked about on the previous episode, check it out if you haven't already. We talked about decoherence in terms of the universe, in terms of things being quantum mechanical, but when you zoom out, it appears more classical, like more coherent on a classical level from what you see. So I guess so how do we kind of relate, how do we relate like this like small, what people typically think is a very small scale thing, to something larger scale as like the universe or even humans for that matter?
Let, let me take a step to at least frame this question a little bit, right?
Yeah.
Yeah. So when we think about physics, like quantum physics seems to be the law of the small, and human seems to be the law of the large. There seems to be a gap. Like how can those be related? And if you look at it from a cosmological lens, there's actually a very simple relationship because, as we know, the Big Bang theory, which is the best theory we have describing the evolution of the universe, tells us that the universe happened to be a lot smaller. And as we just mentioned before, the smaller something is, the more relevant quantum mechanics is. So that means if we go back in time to look at what the universe looked like, the earlier we go back, we do a kind of like a archaeology, his historical understanding of the universe. The earlier the universe is, the more relevant quantum physics is, and it is through this understanding that we find that it turns out that quantum physics is completely. It's so important in the early universe, right? Like the way we understand and know physics, its properties are dictated by quantum physics.
Can you give examples of? I mean, it sounds obvious, but like what I would to really appreciate the significance of that. Like how does that work in some sense?
I think the best way to think about it is just in the simplest way that, as Tim mentioned, if you take the idea of the Big Bang seriously, you run the tape backwards, the universe gets smaller and smaller and smaller and smaller. So even regions that are as big as, the space between galaxies, if you go far enough back in time, just extrapolating the Big Bang, eventually you get to a point where the distance between these galaxies is squeezed together so much that literally it's at a quantum mechanical scale. Um, so I guess the fundamental assumption to this statement is that you can extrapolate the Big Bang back to these distances. And I guess that's the question. Can you extrapolate the Big Bang and the growth of the universe? Can you extrapolate that backwards to the point where quantum mechanics actually plays a role? And what's interesting is that all of the recent evidence that people have been, all the recent measurements in cosmology that people have been making strongly support this idea that you can extrapolate the Big Bang back to the point when the universe is essentially on a quantum mechanical scale. And that actually explains perfectly a lot of what we observe today.
What would be an example of such?
Let me
Yeah.
let me move my head a little bit. If the audience can see the background,
Yeah.
should we
So
explore?
if you take a look at Tim's background,
It's right here.
this is kind of the crowning achievement of modern cosmology is this measurement that you see in the background of Tim right there. It looks kind of like an egg with lots of different colored splotches. And this is what we refer to as the cosmic microwave background, or the CMB. So what is the CMB? Right? You might know that if you look far out at distant stars, in a sense, you're actually looking back into time, right? Because light travels a finite speed. And so when I'm looking at the star, I'm actually seeing how the star looked, a million years ago if the star is a million light years away. So looking out is looking back into time. Does that make sense?
Yeah, I think so.
Yeah.
That's reasonable.
Okay, I think that's so. If you buy that looking out is looking back into time, then the next part you have to understand the CMB is, as the universe goes backwards in time, it gets smaller. We know this from measurements. And as it gets smaller, it gets more dense. So the amount of empty space disappears and basically space becomes more dense. If you run the tape backwards far enough, you see the universe shrinks. All of the matter in the universe is kind of crushed into a smaller and smaller area. The universe gets more dense. As you run the tape back, eventually you reach a point where the universe is no longer transparent. And that is the farthest back you can look back in time, because before the universe was transparent, light wasn't free streaming. So what I said about looking back into time, that stops being true once you look far back enough that the universe is no longer transparent. So basically it looks like a wall. If you look out there, it's like a wall that represents the farthest you can possibly see, given the assumption of the Big Bang. And if you take a picture of this wall, there's a very interesting pattern on there, and that's what's kind of painted on this egg-shaped thing behind Tim.
Huh. So I guess like I'm curious, like why thanks, Tim, for moving your head. I guess like one thing I'm wondering is like it's not exactly uniform. Like certain spots seem more splotched than others. There's certain dark spots. Like, can quantum mechanics explain that, or like what's going on with that?
Yeah.
Quantum mechanics could explain that, but maybe we should because one thing that's not notable in this picture behind Tim is that this picture is like hyper resolution optimized or whatever.
Yeah.
If you actually just look at this picture with your, with the naked telescopes or whatever, it's actually uniform to the better part of like one part in 10,000,
I think yeah,
I
one part
believe.
in 10,000 roughly. You cannot
Yeah,
see
so these
this. Yeah.
fluctuations that you're seeing, are tiny, tiny, tiny fluctuations on top of an incredibly uniform uh, background. So, okay, now
Oh,
going back to your question about these fluctuations, does this picture give evidence to the fact that there are quantum mechanical effects going on in the beginning of the early universe? That's the question.
Yeah.
yes.
I think it does. I think it does. And for these following reasons. So first of all, if you just look at this image of like cold spot and hot spot, and these do really correspond to temperature, because this is basically an image of what the plasma look like. It's a translation of an image what the plasma of the universe looked like in its early stage, right? Before galaxies were born, before any stars were born, universe was just a hot plasma, right? So in this regime, we have hot and cold spot here, right? And now so this picture is obtained if you look along like any direction into space into the universe, right? You see these hot and dark spots, and those correlate perfectly, perfectly after some mathematical extrapolation. They correlate perfectly to where galaxies are and where galaxies aren't, right? So you can say that, hey, where there is a hotter spot, that's where there's more galaxy, and where there's a colder spot, there's less galaxy. So we know that these fluctuation of density correlates with our existence, basically existence of stuff, right? But of course, that itself is not quantum mechanical, right? This is just classical physics, heat, hot plasma, and kind of like cooling down, structure formation. The question is, when you extrapolate even further back, right? You know that in this plasma there's hot and cold spot. Well, where do those hot and cold spots come from, right? And
Hmm.
it turns out that if you use quantum physics, it actually explains very well the statistical properties of those fluctuations.
Huh. What do you mean by statistical property of the fluctuations?
Yeah, maybe one way to put it is that in quantum physics, oh, okay, yeah, maybe okay, let's go through it from a more data-driven lens, right? If
Hmm.
you just look at this picture, it looks seemingly totally random, but there are actually subtle correlations between the spots, right? If you say that this spot, like for example, this spot right here, it's a little cold. What is the chance that another spot some distance away is also cold, right? If you say that this
Hmm.
is if there's no correlation, if there's no interesting statistics, you might not expect anything. But like, well, why would one spot of the universe care about another spot of the universe? Like, why would they care at
Hmm.
all, right? And remember, these are like you're looking at distances super far away, right? Like they could be millions of light years away, whatever. They could be completely should be unrelated, right? But it turns out though there is a correlation, and this correlation depends on how far the distance is. And if you just gather all these little correlations together and summarize them, you get what we call some kind of a power spectrum. Basically, a relationship of correlation as a function of distance. And
Hmm.
that's not entirely expected from just like normal physics, right? And
What?
so mhm.
Oh, sorry. Go ahead, Tim.
Yeah, well, let me just add one more word. And the way to explain it is that these are actually quantum correlations. These are basically there's some entanglement to some extent between them, and that's why they're correlated.
Gotcha. So two things I want to ask about this, about what you just mentioned. One is, can you give our audience a scale of like how big this thing is? Because it seems like, is this the observable universe? Is this like smaller than that? And then the second is, what is the difference between classical correlations and quantum correlations with respect to this? Like, I would expect nearby points to be correlated with each other, but is there something more to that than just that?
So when we think of the scale of this, it's we're really talking about like the angular scale. So this picture that is kind of flattened into an egg shape, you should think of that as actually being painted on um, on the boundary of the universe in every direction you look.
It's enormous. Let me just put it that way. It's in freaking enormous. It's like 10 billion light years. How many billion light years across? It's like freaking enormous, right? I don't even know the numbers.
Yeah.
These pixels are like, you think it's just one pixel? Oh boy, you'd be wrong. This one pixel, it represents like clusters of galaxies. This is ridiculous, right? This picture.
That's fair. Okay, so unimaginably huge is what I'm getting.
Right, and
Okay.
basically that's why these correlations are actually not so obvious, right? Because like this direction that's in front of me in this universe. Imagine I just shoot a laser beam in direction totally in front of me, like shooting it super far, and direction behind me, super far. Like there's no reason they're related in any way, right? Like these are like billions and billions of light years away. Like why the heck would I expect any correlation, let alone a pattern of correlation? I mean, this is super strange to some extent.
Yeah, that is strange. How does quantum mechanics explain that?
Well, the quantum mechanics tells you that when things are entangled, there could actually be correlation. And this is kind of related to what is it, Einstein's thought experiment, that correlation could actually travel, in some sense, faster than the speed of light. But as long as the correlation is not a propagation of signal. This is when Einstein felt really uncomfortable with quantum physics. He said that, oh, this feels like spooky action at distance. But we actually measured that, literally, right? Like, one part of the universe is correlated with another part of the universe. And, the only way I think we know how to explain it is it's got to be some quantum physics. Well, of course, there's more physics to it, right?
Yeah, actually, all of the points here are very correlated with each other because they're all almost exactly the same temperature minus these tiny fluctuations. That's the first peak in the power spectrum.
Yeah. I mean, I guess there's another piece, right? Like, even with quantum physics, it's still not obvious that it's so uniform. I mean, that's another problem that we haven't described yet. But
yeah, the elephant in the room here is inflation, right?
Yeah.
Before we get to inflation, you guys have mentioned the word power spectrum several times. What does that mean in this context?
It just means that there's a correlation between two different totally unrelated areas of the universe. How much, like imagine just be like, this spot has some galaxy. What's the probability that another spot, I don't know how many billion light years away, also has some galaxy, right? And this function of probability as the amount of distance varies, that's called the power spectrum. And we can kind of literally measure it, right? When we look at all the when we map out our universe, we can actually measure it. Be like, hey, here's a galaxy in some distance away. Here's another galaxy this distance away, and then we can just average it statistically. You can think of it as like, what is the average distance between kind of unrelated galaxies? You know, these basically captures the statistics of our universe. These are what we call the power spectrum of correlations.
I see. So it's a way of capturing the statistical correlations between different points in the universe.
Yeah.
Gotcha. And then before we move on to inflation, last question is, are you saying like, no matter kind of which way I look in the universe, whether I look here, Australia, China, India, or any like other place, I'll see this very similar CMB type background?
Yeah, well, I mean, because this is an imprint of the entire universe. So yeah, you see it. This thing is, you gotta observe it from like the whole Earth, every direction of the Earth. You're gonna have to.
I see.
Basically, this is measured by launching a spacecraft into space, I think, right? And then just like taking a tiny snapshot at every angle, in great detail, and just kind of like slowly patch this enormous image together. Basically, it's probably like the highest pixel image in some measure, probably.
Wow. And then you would also have to capture this in like very long wavelength photons, right? You'd have to, because I assume these are extremely long wavelength photons.
Yeah, these are not your visible light. These are very, very low frequency, very, very large, very much large photons. So these are not your typical, like the coloring, obviously. It's rendered. It's not exactly, So
Yeah, which explains minus light pollution why I wouldn't be able to see it if I looked up at the night sky.
yeah, unless your eyes have what is it, liquid nitrogen cooled and like super calibrated, I don't think you'll be able to see them with the naked eye. Not even close.
Yeah, it is
I
kind of
see.
unfortunate that this projection makes it so difficult to see what it is, but we should really imagine that this is like an egg, and we're kind of like at the center of the egg, at the center of the three-dimensional egg. And if you look out, like if I look directly up, maybe I'm looking at one of the cold spots, one of the underdensities, and if someone in China is looking directly up, they might be staring straight at one of the hot spots, one of the overdensities. And as Tim mentioned, this directly correlates to the number of galaxies you would also see if you looked up. If you're looking up and there's a hot spot right above you, you would count the galaxies there, and you would see that there's a huge number of galaxies there. If you look up and you see that there's a cold spot, you count the galaxies there, you would see that there's an anomalously low number of galaxies there. So these are really like the seeds. These overdensities are the seeds that form what we call clusters of galaxy or superclusters of galaxies. So that's how, if you believe that the origins of these things are quantum mechanical, then it directly ties the evolution of structure, the evolution of everything to quantum mechanics, including us.
Wow. Yeah. So I guess like you guys mentioned the word inflation. What the heck does this have to do with anything?
Yeah.
Is monetary inflation? What are we talking
I think
about
this is way worse than monetary inflation. I mean, but by worse, I don't mean in any moral sense. I mean that it's an even, like, I mean, we look at inflation right now. It's like, I don't know, a few percent rate of inflation, right?
Yeah.
We're talking about looking at quantum mechanical fluctuations, or at least things that relate to quantum mechanical fluctuation. That is the size of the universe. I mean, that's insane, right? Like, when we talk about quantum physics, we're usually talking about tiny things that like will fit like within maybe a handful of atoms, right? Like, that's typically what we mean when we talk about quantum fluctuations when doing experiments on Earth, right? But it's kind of insane that somehow you grab this picture of our entire freaking universe and we see quantum fluctuations. Like, holy crap, like, this is insane. So basically, the way to explain it is because there is a period where our universe is...
Wait. Before you describe what inflation is, let me just say one thing, is that, like, there's a problem with this idea that Tim just mentioned, right? I want to hammer this point a little bit before we go on. So quantum mechanical fluctuations, as Tim mentioned, happen on microscopic length scales, 10 to the minus 34 centimeters or whatever. If you just assume that the Big Bang is just your average expanding universe, if you just assume that it's expanding at in some normal way, like extrapolating back, it's actually impossible that you could have quantum mechanical correlations on this kind of a length scale. What we're observing here is, so right now our universe is like 13.6 billion light years across. When this picture was taken, it was only 186,000 light years across. So it was 1,000 times smaller. This is a picture of the universe when it was 1,000 times smaller. But it's still pretty big. It's still 186,000 light years across. How is it possible that you can get quantum mechanical fluctuations to appear on a scale of 186,000 light years when they're supposed to be reserved for the smallest of length scales? That's kind of a puzzle. But it turns out if you just make one extremely simple assumption about the state of our early universe, you get all of this for free.
Whoa.
And that's what I'm going to explain.
I like three things. Tell me more.
Yeah, well, the free thing is not really free, but it comes with inflation, and this inflation, I think it's really justly named. It's the greatest inflation in the universe, basically. Basically, the idea is simple: is that the universe was even smaller than we thought, but it underwent a period of hyper duper inflation. It got blown up so quickly that these fluctuations didn't have a chance to just be destroyed or decohere in some ways. That it just get blown up to this enormous proportions, right? And that's why you see like these correlations that are across light years apart, right? And this goes under the theory of inflation. This is an assumption, right? It hasn't been totally verified, but you have such strong evidence that this is the case.
Right. Inflation is basically the idea that in the very early universe, so right now we observe the universe to be expanding in, roughly a linear fashion for most of the history of the expansion. And if you just assume this kind of linear expansion, as I mentioned, it wouldn't be possible to stretch microscopic quantum mechanical fluctuations to this kind of macroscopic length scale. But if you just make this very simple assumption that there was a period of time in the early universe where the expansion was exponential, then it guarantees that quantum mechanical fluctuations would be stretched to this time scale. And the reason inflation is not just some idea that people came up with to explain this. It's a puzzle why our universe is not expanding exponentially right now. Exponentially expanding universe is a much simpler universe than the one we observe right now. So if you assume that the physics of the early universe was simple, it's a very reasonable hypothesis to assume that there was some period in the very early universe where it was expanding exponentially. And then you would have to see what we see here.
Wow. So when you say like theory of inflation, does it include this exponential expansion, or is it just the phenomenon of the universe growing with time?
Inflation refers specifically to this exponential period.
Yeah.
I see.
Yeah, and I would argue that this theory of inflation it's a very natural universe. When you look at most universes, and you have to use quantum physics, most universes are quantum mechanical. Quantum mechanical effects will cause this exponential inflation, right? Basically, the quantum mechanical fields and the energy in these quantum mechanical fields will just kind of exponentiate by itself, right? And so this behavior is very typical, like Mikey said. So we generally expect, any random universe to behave something like that. The interesting thing is at some point this seems to have kind of stopped, and somehow create interesting things, and somehow these and as a result, the minute quantum fluctuations get amplified, structures form, galaxies form, and ultimately leads to us, right? So that's the real puzzle here, basically.
Yeah, it's worth mentioning that if you go into the infinite future, the universe will again be expanding exponentially. So exponential expansion is a very natural way for the universe to want to be. We know it's going to happen in the future. It looks like it happened in the distant past. This period that we're in right now is kind of a weird period where this exponential growth has stopped for a brief moment.
Huh. So actually, I want to ask a question about what does it mean for exponential growth? Because my understanding of inflation is that like everywhere in space is expanding at the same rate. So if I imagine I'm like really far away from another object, we're like moving faster and faster away from each other. And so when you say inflation is increasing exponentially, what does that mean in that context? I already thought it was exponential even right now.
No, right now it's not exponential. So as Tim mentioned, it's kind of an interesting effect.
Yeah, it's becoming, but yeah.
Yeah. So there's a number of things that affect the way the universe expands, and one of them is the dominance of quantum mechanical. Oh gosh, I'm going to screw this up. So basically energy causes the universe to expand, okay? But there's a certain type of energy, which we call quantum mechanical energy, that comes from empty space itself. So as space is expanding, you're making more space, and that's creating more energy, thus driving the universe to expand. So it's like this positive feedback loop, where each region of space is expanding, each region of space is therefore containing more energy from quantum mechanics, and then that in turn drives the expansion outwards. The only thing that can slow that down is the presence of matter. the presence of matter causes a change in this kind of exponential expansion and slows it down briefly. But as the universe expands, the matter gets diluted, whereas the quantum mechanical energy density is staying constant. And so that's why you get this kind of behavior of exponential expansion followed by a slowdown, followed by exponential expansion again.
Wait, I thought like I understand that there's like this major exponential expansion in the beginning, but isn't what you just described exponential expansion, but very slow exponential expansion? Like you're at the beginning of the exponential, and then we'll just
No,
keep
it's not.
increasing.
Yeah, that I can see why. Yeah, it's not quite like that because
Okay.
the key quantity is the energy density. So you can ask the
Oh.
question: how much of the universe's energy density right now is due to matter, and how much
Hmm.
of it is due to quantum mechanical energy?
Hmm.
If the energy density of matter is greater than the energy density of quantum mechanical energy,
Hmm.
then you're not going to get exponential expansion. It's a polynomial expansion. But
Hmm.
once the energy density of quantum mechanical energy starts to outweigh the energy density of matter, then
Hmm.
you start to get this kind of exponential growth again. And so it's like a kind of a careful balance. We actually live very close to a turning point of when the energy density turned over from being matter dominated, as we say, to quantum mechanical energy dominated.
Oh, exciting. Exciting stuff. So I guess like we're very close at time. I guess where does this leave us? Like, does like yeah, coming back to original question of quantum mechanics giving rise to humans, how would you tie this all back together?
I would say quantum mechanics is critical in our existence. Even though right now it doesn't seem like quantum mechanics plays a big role in our everyday lives, but this is kind of like a Goldilocks situation, right? A typical universe will be quantum mechanics dominated. Everything you see is kind of highly quantum mechanical. We're kind of for some reason sitting in this really sweet spot of temporary domination by things that are non-quantum mechanical. And by non-quantum mechanical, I just mean like a macroscopic aggregation of quantum mechanics in such a way that there's a coherent sense of reality that exists, right? Whether that's selection bias is because we're here or not, we don't know. But like, just but I want to re-emphasize that just because we're at this Goldilocks zone of like reasonable existence does not mean that we should forget about quantum physics, because at any moment, in the history of the universe, it can do total violence to the structure of the universe, and that's what we expect in the past and in the future.
I see. Any thoughts you want to add on that, Mikey?
Uh, yeah, I mean, just going back to the original question, I mean, this is what we call the standard model of cosmology. This picture of exponential expansion. I mean, so if you look at a very small region of space, you'll see quantum mechanical fluctuations, right? Virtual particles and antiparticles popping in and out of the vacuum. Um, if you just assume that there's some exponential expansion during this time, then these quantum mechanical fluctuations get stretched out to huge length scales. If they weren't there, there wouldn't be these spots in the CMB. Then galaxies wouldn't have clustered together. It basically wouldn't have been possible to form structures in the universe without these fluctuations. So yeah, I think this is the interesting way in which we can say that our existence arises from quantum mechanics, aside from the fact, stability of atoms, blah, 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 or nonsense ideas like quantum consciousness. This is like really the deep way which we can look back in time and see that
Yeah.
quantum mechanics, kind of creating the fingerprint for the structure we see in the universe
Yeah.
today.
Yes. So basically, we are all children of quantum fluctuations. That's it.
So should we on Father's Day and Mother's Day actually give gifts to the quantum
The
fluctuations?
quantum overlord. Yeah, we're probably just the same tiny patch of quantum overdensities. You know, all,
I mean,
all
they're
of us.
literally our farthest ancestors.
Fair, fair. Well, any last thoughts you guys want to add, or should we call it here?
I'm not going to summarize any better or different.
Fair enough, fair enough. All right then. Well, on that note, I want to thank you for joining us, and we'll see you all next week.
Yeah. Thank you all for joining.
Yeah.
Bye.